Let's take a look at our comparing means practice lab. Here's the problem. A large highway runs through the small town of Middleburg. As the highway enters the town, the speed limit is reduced from 55 miles per hour to the residential limit of 35 miles per hour. However, many motorists drive through the town at much higher speeds, raising safety concerns. The town council has the idea of putting up a sign that reads, "Begin slowing here," a half mile before the town line. They want to know if this prompting sign would produce a significant change in motorist speed. Before the sign is introduced, a hidden speedometer records the speeds of 50 vehicles as they cross the town line. After constructing and placing the sign, the hidden speedometer is used again to record the speeds of another 50 vehicles. Descriptive statistics for these two sets of observations are provided below. Let's talk about this a little bit. What we have here is an experimental design. Now, this is an experiment rather than a correlational study because they have manipulated the independent variable. So if we were to talk about this in terms of independent and dependent variables, right? So remember that your independent variable is theorized to predict or cause some change in the dependent variable. In this case, the independent variable is the sign, and the dependent variable is the speed. So the logic here, or the theory here, is that the introduction of the sign will cause the motorist to change their speed as they drive through the town. The independent variable is manipulated. So at first there is no sign, right? So let's see, before the sign is introduced, so we have a before condition. They measure the speed of 50 vehicles, and then after the sign is introduced, they record the speeds of another 50 vehicles. So we have before and after, so with the sign and without the sign. That is our independent variable. It has two levels. So we have a without condition measured first, and we have a with condition measured second. There we go. So we have independent variable with two levels, without and with, one dependent variable, which is speed, which is measured in both conditions. This is an experimental design because the independent variable is being manipulated by the experimenters. Okay, let's go forward. They've recorded the speeds of these vehicles using a hidden speedometer. Now, from a mathematical standpoint, this isn't strictly relevant, but I still think it's worth pointing out. Anytime you take measurements in a situation, a behavioral science situation, you run the risk of impacting or changing the thing that you're measuring. Let's suppose this weren't a hidden speedometer. Let's suppose it was one of those big signs that you see that lights up and flashes the speed of you're going as you drive by. Right. So the fact that the speed is being measured using this very conspicuous measurement could prompt them to slow down. They see that their speed is being flashed at them. That might be the thing that gets them to slow down rather than this prompting sign that says begin slowing here. So it would be really hard to know whether it was the prompting sign or the speedometer that was causing the difference if this were not a hidden speedometer. So it's important that it's a hidden speedometer. We're trying to isolate the effect of the independent variable, the begin slowing here sign, by keeping everything else constant and not introducing some other variable that could have some impact on our results. So this is the situation. Down here we have a table summarizing the results. This table has 4 columns. First we have the condition. So the prompting sign condition is the first level is without the sign, the second level is with the sign. It's also giving us the averages for the total, all 100 together. We have the means for each group. So the mean for the mean speed without the prompting sign is about 47.8 miles per hour. With the sign, 34.6 miles per hour. And then the total, this is everyone together, 41 miles per hour. N is the sample size. So we have 50 without the sign, 50 with the sign, and 100 all together. Over here on the right, we have the standard deviation for each row or for each condition. Without the sign, the standard deviation is 11. With the sign, the standard deviation is 8. So what does this mean? We can see that there is a wider standard deviation in the without group than the with group. So lower standard deviation means that the values are more compact, they are more consistent. So drivers are a little bit more consistent, more alike as they go through the town when the sign is up. Without the sign, there's more variability. Some are going faster, some are going slower. There's more spread. There's more uncertainty in how fast the drivers will be going through the town. So this is our raw data here. The goal of this analysis is to determine whether the addition of the prompting sign significantly affected the average speed of motorists crossing the town line. Is there a significant difference? So we're just looking at the observed values, so you can see a difference in the observed means. We're looking for whether there's a significant difference. Now we could talk about statistical significance, we could talk about practical significance. When we don't see a qualifier in a statistical context like this, we can more or less assume that we're talking about statistical significance. We're going to look at the p-values and determine whether this is a statistically significant difference, but it is also good to look at the practical significance. What's the effect size? You might find that the sign reduced the speeds, but it wasn't by enough of a difference for us to matter, or maybe to justify the expense of putting up the sign or maintaining the sign. Let's take a look at our hypotheses. The town council suspects that adding the prompting sign will change the average speed of motorists crossing the town line. Notice the language, change. So what we have here is a bidirectional hypothesis. We're just saying that the sign will make the speed different. We sort of intuitively expect it to go down, but we're also open to the possibility that the speed could go up. Maybe something about the sign prompts drivers to speed up, or perhaps there's no change at all. So the null hypothesis is no effect, that putting the sign up has no impact whatsoever on the speed of the drivers. So the speed without the sign is exactly the same, or statistically I should say the same, as the speed with the sign. All right, so we're talking about the null hypothesis. We're talking about the population, that out there in the theoretical population of all the cars driving through the town, the speed without the sign is the same as the speed with the sign. And when we want to talk about the mean of the population, we use the Greek letter mu. Kind of looks like a cursive M a little bit between that and a U. So that the mean of the sign without, so I'm going to use subscript here, mean of without, there we go, is equal to the mean with the sign. Okay, so mean without equals the mean with. That's what our null hypothesis is. There's no effect. The sign makes no difference. Now the alternate hypothesis is that there is a difference, that there is a change. Could go up, could go down. In other words, that the means are different. If this were a directional hypothesis, if we were to say we're expecting the mean to go down, right, it's going to reduce speed, and we're only looking at that possibility, then we'd write this a little bit differently. But here we're simply saying the null is that they are the same. The alternate is that they are different. In other words, they are not equal. And we're talking about the mean of the sample that we have in front of us, the data we've collected. So we're going to use the symbol x bar, which is just x with a line over it, and that is the symbol for the mean of a sample. So the mean of the without sample does not equal, so it's an equal sign with a line through it, the mean of the with sample. There we go. So these are our hypotheses. The null is that there's no effect, that the two means are the same. The alternate is that there is an effect, the means are different. The means are not the same. Okay? The assumptions. So before we get into a statistical test, there's always certain assumptions that we have to consider. If the assumptions are not met, we cannot have confidence in our results. And there are three assumptions that we're going to be looking at when we're testing the significance of the difference between the means. And these are going to be a normality, assumption number 1, absence of outliers, assumption number 2, and homogeneity of variance, assumption number 3. So let's start with normality. In order to ensure that the observations for each variable are approximately normally distributed for each group, we'll inspect a histogram of each distribution. Histograms are univariate graphs, and that means that there is only one variable represented here. In this case, with the first one, let's see here. This is the speed and the without condition. Okay. So there were 50 different observations that took place before the sign was put up. And here is that distribution. So we have this, the curve here is the theoretical normal curve, and we're going to be comparing the actual observations against this theoretical curve and talking about what we see. So this is the before, this is the after, or the with the sign condition. And let's take a look. So here it looks like the observations more or less follow along the curve. Over here, it's similar. Notice that there is a little bit of a skew. We have more observations over here on the left side, on the slower end, but we do have some that are quite fast, right? So we have a few that are still on the high end. So we have a little bit of a skewed distribution. A skewed distribution is where it's not even like the bell curve, but it's higher one end and kind of drags out on the other side. And the skew refers to the tail. So this would be a positive skew, a moderate, like a slight positive skew, or you could say it's skewed right. So remember, the skew refers to the tail. It spreads out a little bit this way. So there is a little bit of a positive skew, but we're looking for very egregious violations. If it's only a problem if it really departs from normality, would be something, I'm going to kind of draw on this, so something where it's like up here and then goes way out there. There's observations way out here. Most of them are over here. Right, way skewed. That's what we're concerned about. Here, it's still approximately normal with a moderate positive skew. So it says, describe the shape of the two distributions. Has the assumption been met? Let's go ahead and talk about that. So a visual inspection, right? So we're not looking at the numbers here. There are mathematical ways of evaluating the skew and the kurtosis of these distributions. The kurtosis is how pointy or flat the distribution is. The skew would be pulling it left or to the right. So there are mathematical ways of going about that and rules of thumb for interpreting those. Here we're talking about a visual inspection of the two histograms. Revealed that both distributions were approximately normal. So approximately normal, that's an umbrella term. That's a little bit subjective, but we're saying it's more or less along those lines. It's not a radical departure from normality. Although the with condition, right, so that's this one here. So we're going to go ahead and mention that there's a bit of a skew, demonstrated a slight positive skew. There we go. So we have a slight positive skew over here. It's nothing too extreme. Over here again, a little bit of a negative skew. If we were going to talk about a skew, there's slightly less observations on the left than we have over on the right, but approximately normal. So for that reason, the assumption of normality has been satisfied. There we go. So the assumption's been satisfied for both distributions. All right, moving forward, absence of outliers. We'll also inspect the histograms for outliers. Are there any observations that appear to be problematic? Has the assumption of absence of outliers been satisfied? So we're going to go about that using the same visual data here. When we talk about an outlier, we're looking for a situation, if we're looking at a histogram, where there is you have almost your last observation, then some white space, and then another observation over here to the side. So let me show you what that would look like. All right, so let's suppose this graph continued this way, this histogram. We're at about 25 miles an hour right there. Let's suppose, let's see, here's 10. Let's say somebody was going down the road at 5 miles an hour, right over here. Let's pretend we had an observation right over there, okay? And suppose that we're 5 miles an hour, okay? So we have almost everyone between 25 and 65 miles an hour, fairly normal distribution. Then you have this wide space, nobody 20, nobody 15, nobody 10. All the way over here, we finally get to somebody driving through the town at 5 miles per hour. This would be a potential outlier. Okay. Conversely, you could go on the other end, right? So here's 60, 70, 80, 90, right? Let's suppose that 90 were over here. And let's suppose you had somebody careening through town at 90 miles per hour. So Speed Racer is flying through here at 90 miles per hour. This would be another example of an outlier. Right, you have everyone else is over here in a whole long white gap, and then finally you have the other case. You could even have a couple of outliers. Maybe somebody was, his buddy was also driving through town. There we go. was also driving through town with him at 85 miles an hour. He was losing the race here, right? You could have a couple of potential outliers. Right? So this is the kind of thing we're looking for. There's a big gap, and then we have some observations way out here on the end. This would be problematic because this could have, what this is going to do is increase the variability within the sample, which is going to increase the standard deviation, and that factors into our equation when we're calculating statistical significance. It's going to make it harder to find statistical significance. It's also going to skew the mean. Right? So the mean is going to be very susceptible to outliers. It's not robust to that, so it's going to have an influence on the mean. It's going to affect the calculation of the variability between the samples. Can make it seem that there's not a statistical significance when maybe in fact there is. Causes issues. So we're taking a look for those. We don't see that, so we'll go ahead and delete all this. There we go. So we're okay as far as outliers go. All right. So we can again say a visual inspection of the two histograms also revealed no apparent outliers. The assumption of absence of outliers has been satisfied. There we go. Okay, so I just wanted to draw in what that would look like so you'll have a trained eye for the future. Sometimes students will see they'll look over and see something maybe right here and get concerned on the other assignment. I don't want you to have to worry about that. So if we had an observation right here, okay, even if there were a little bit of white space right there, this would still be fine. It's actually would be part of this kind of this moderate positive skew here. This would not be considered an outlier. Okay, you have to get a little more white space. Probably would need to be over here before we'd start to consider that an outlier. Even there would probably be okay because it's sort of part of this general skew that you see sliding down here. Okay, moving on. Homogeneity of variance. So homogeneity of variance means that the variability in the two groups is statistically the same. So how spread out the observations are. Okay. So we know that there's more variability in the without group, right? So there's a standard deviation of 11 versus the with group, a standard deviation of 8. But is there a statistically significant difference between these two? If there is, we have to correct for that. The way we check for that is using Levene's test for equality of variances. When you run a t-test, which is what we're dealing with here in SPSS, it's going to go ahead and run an independent samples t-test. Let me clarify. You're an independent samples t-test in SPSS. It's going to run this test for you, Levene's test for equality of variances, and then we'll interpret this. Students often have a lot of trouble interpreting this. All right, so what they're testing here is to see if the variability, so let's kind of draw it out here. So let's suppose that this is the variance for the first group compared to the variance for the second group. All right, let's just suppose those are our two distributions. Is the variance here significantly different than the variance here? We know that our cutoff for statistical significance is p is less than 0.05. So we're asking the question, is p less than 0.05? Right? If it is, then there's a significant difference. If it's not, then there's not. So over here, significance, so this is our p-value for this test, is 0.109, right? So that is not less than 0.05. So 0.109, that's 10 hundredths, is not less than 5 hundredths. Therefore, it is not statistically significant. In other words, these are not significantly different. So they are statistically equal. Okay, so if this were less than 0.05, then we say there's a significant difference between the two variances, and we'd have to use a corrected t-test value. But here, they are not significantly different because this is not less than 0.05. Right? It's not less than 0.05. So Levene's test is non-significant. They're not different. They are equal. Therefore, the assumption is satisfied. So the significance value for Levene's test is 0.109. Is the test significant? Let's go ahead and talk about that. Levene's test was not statistically significant. So P equaled 0.019, right? Because it was not less than 0.05. Okay, so it's not statistically significant because it was not less than 0.05. Okay, this means that the variance of the two groups, of the two conditions, the two conditions, the two samples. Let's go with this, with the two samples. This means that the variances of the two samples were equal. The assumption of homogeneity of variance was supported. Okay, so the assumption, homogeneity means the same. So the assumption is that the variances are the same. How spread out this is the same as how spread out this is. Since they're not significantly different, then they are therefore the same. The assumption is supported. Moving on to the t-test analysis. To compare the two means, we will use an independent samples t-test. The SPSS output is provided below. There are different types of t-tests for different situations. Here we're dealing with an independent samples t-test because these two samples, the before and the after, the without the sign, the with the sign, were collected independently. The cars aren't matched up with each other in some way. For example, it was not Bob drove down the street without the sign and then Bob drove down the street with the sign, and you compared Bob's score before to Bob's score after, his speed before, his speed after. That's not what's going on. You have 50 random cars, you have 50 other random cars. These samples are independent of one another. They're not connected or linked up in some way. Therefore, we're dealing with an independent samples test. A classic example of a dependent samples test, right? A dependent samples would be if you were doing maybe a math test and you had students in the math class, you gave them a test, then you taught them some material, then you gave the same students the test, and you would match up their scores before and after. But that's not what's going on here. You can't really match up the same cars. They're just different people driving through town. So we have an independent samples test, and here's the output. So the first thing they're going to give us is the descriptive statistics table. This is the mean of the two samples. This should look familiar. Okay, so 3.6, 34.6, 47.8 should be the same, 34.6, 47.8. So this is the same information we've already encountered from the first part of our t-test. It says, examine the descriptive statistics table above. Which observed mean is lower and by how much? What does this mean practically? Okay. So it's the same information that we've gotten before, but it's asking us to explicitly consider which mean is higher, which mean is lower. This is important because sometimes students will run a t-test and they have in their head which way things are going to go, which mean is going to be higher. Maybe they're comparing males and females, athletic ability. And they sort of assumed that, well, the males are going to have higher athletic ability. When they find a significant difference, they just conclude, oh yes, my hypothesis was confirmed. Males have better athletic ability. But it could be that the females have the higher athletic ability, and they only focused on the significance level of the t-test without paying attention to the descriptive statistics. So always take a look at the descriptive statistics first and see which observed mean is higher before you go and examine the p-values. So let's take a look here. Which mean is higher, which mean is lower? So without the sign, 47.8, with the sign, 34.6. Remember, we're talking about miles per hour. So before they put up the sign, the average speed of people driving through the town was about 48 miles an hour. What was the speed limit? Do you remember? The speed limit is 35. So they're driving along at 55 miles an hour. All right, so if we were to draw this, right, so they're going along, hunky-dory, 55 miles per hour speed limit, right, and then they get to the town, right, the town's over here. That's a nice town, kind of looks like a histogram. Over here, now the speed limit drops to 35 miles per hour. Okay, so here's how fast they're supposed to be going. We're measuring their speed right around here. They're supposed to drop speed from here to here. So let's see what happened. So before they put the sign up, people were cruising through town an average of about 48 miles per hour. But after they put the sign up, their speed dropped to 35 miles per hour. So it looks like the speed went down. They put up the sign, it dropped by about 13 miles per hour. Right? So let's go ahead and comment on that. Let's see here. Okay, so before they erected the sign, the average speed was 47.84 miles per hour. After the placement of the sign, the average speed dropped to 34.62 miles per hour. The observed mean was lower after the sign was erected. Okay, so how much lower? Let's see here. It was about. Let's do the actual math. It's instead of saying about, why not just give the precise number? You know, we have calculators. We can work this out. 34.62, 13.22. So it was 13.22 miles per hour lower after this sign was erected. So what does this practically mean? It means that it's dropped by, let's see here, over our standard deviations. Our standard deviations range from 8 to 11, so we're going to be over that. So it looks like a pretty substantive drop. 13 miles per hour, it's a decent difference, and it's gone down. Well, what else? It went from, let's see, 35 is where they're supposed to be. Right? So they went from well over to just under the speed limit. So practically speaking, the average driver is now going the speed limit through the town rather than going way over the speed limit. So we want to make a note of that. After the sign was placed, the average driver traveled the speed limit through the town. So it appears that it worked. They were going too fast before. Now they're going under the speed limit. So far, so good. Right. So we always want to take a look at the descriptive statistics and think about what this means practically before we get into the significance test, looking at the p-values. Examine the t-test results above. The significance level of the test is 0.000, or p is less than 0.001. Is the difference between the means statistically significant? What does this mean? Should we reject or fail to reject the null hypothesis? Okay, so let's take a look at this table. Here's our test statistics. They've run a t-test, an independent samples t-test. And when you run a t-test, you have a test statistic, which is 6.739. Happens to be negative, but the sign doesn't really matter. It just depends on which sample you put first in the equation, but it's going to have the same significance level, whether it's positive or negative. We have the degrees of freedom, which is the sample size minus 2, because there's 2 samples. And then we have the significance level, so 0.000. This is the p-value. And we know that the cutoff is 0.05. So we asked the question, is p less than 0.05? Well, in this case, it's much less. If we were to report this in the next highest cutoff, which is 0.001, we would report this as p is less than 0.001. So this is definitely less than 0.05. It is very statistically significant. Okay, so this tells us there's a high level of statistical significance and the difference between these two means. The mean difference, 13.22. Remember, we worked that out earlier. So this is just subtracting those two. The standard error of the difference, and then a 95% confidence interval of the difference. So we're 95% confidence that the true difference is somewhere between 9 miles an hour and 17 miles an hour. Notice that this range does not include 0. Therefore, we do have significance at the 0.05 level. So yes, it is statistically significant because P is less than 0.05. Focus in on this value right here. Let's write about that. So there was a statistically significant decrease in motorist speed after the sign was erected. And we're going to go ahead and report that. So we have T because it's a t-test. The degrees of freedom is 98. Space equals 6.739. Go ahead and report that. We could also round that to the hundreds place, 6.74. And I left off the negative sign. Again, we're going to have the same value. It's not necessary to include that. Comma. And the p-value, p is less than 0.001, which is the next highest cutoff point. So there is a statistically significant decrease because it was with the sign it went down in motorist speed after this sign was erected. Should we reject or fail to reject the null hypothesis? Okay. So the null hypothesis is that the speeds are equal. But we have evidence that the speeds are not equal. Right? As we looked at the sample, we said, it doesn't look like they are equal. Now, we don't know that for sure. We haven't proven that. We're talking about probability or inference. But we have a pretty good idea that they aren't equal. The probability is low that they are equal. In fact, we can talk about this in statistical terms. Right? What does this mean? Oh my goodness, there is less than a, how would we convert this to a percentage? Right? So decimal 0.001, we would move the decimal places 2 points to the right, 2 places to the right, so it would be 0.1. There is less than a 0.1% chance. Okay, not 1%, that would be if it were here. A 0.1% chance, less than a 0.1% chance that we would generate a test statistic at least this large. We're talking about the 6.739. So we run this test and get this t-statistic when at least this big, if the null hypothesis that the means are equal in the population were true. Okay, so if the null hypothesis were true, out in the population, there's no difference. So if you were to sort of have this infinite number of hypothetical people driving with the sign, without the sign, if there really was no difference, right, and yet we were able to randomly collect these data and come up with this test statistic, this where did it go? The 6.7, there's only a 0.1% chance, less than a 0.1% chance that would happen. It's very unlikely that we would get such a large test statistic if that null hypothesis were true. So because of that, we're going to reject the null hypothesis. But that's why we don't accept the alternate hypothesis. We haven't proven that they're different. We're simply saying it's unlikely that they're the same. In this case, so our threshold is 0.05. We're looking to say that there's less than a 5% chance. In this case, there's less than a 0.1% chance that we get this statistic if that null hypothesis were true. So it's very unlikely that the sign made no difference, that those means are the same. So we're going to reject that null hypothesis in favor of the alternate, and we're going to move forward on the assumption that they really are different. The sign really did have this impact. Okay. Therefore, we will reject the null hypothesis in favor of the alternate hypothesis. Okay, so we're going to reject the null hypothesis. We're going to infer right? We don't know for sure. We haven't proven. We're going to infer that the means are different based on the evidence in front of us. Now, the next question, does this difference matter? So we talked about 13 miles per hour. Kind of seems like a lot. We looked at it relative to the standard deviation, although we're going to look at that a little more closely over here. We kind of eyeballed it. In this next section, we'll look at it more precisely. We saw that it dropped the speed limit from above the speed limit to under the speed limit on average. But let's be more precise and let's be more technical, and let's talk about the effect size. So to assess the practical significance of the difference, yes, they went more slow. They went slower, but does that matter? Calculate the effect using Cohen's d. Because this is a pre-post experimental design, you can use the standard deviation of the pre-test condition, that is without the sign, in the effect size equation. So what's going on here about this pre-post design? So the effect size is the difference between the two conditions, between the two samples, divided by the standard deviation. Now, if the standard deviation is the same, that you know exactly what to use. In some situations, you might use the pooled standard deviation, where you kind of average them together. But in this particular situation, an experimental design, a pre-post experimental design, we use the standard deviation of the pre-test condition. So we go back to our statistics, our descriptive statistics. The pre is the without, which is 11. Okay, so we're going to use this standard deviation when we are calculating the effect size, because reducing the standard deviation is actually part of the effect. So this is what the variance looked like before, without the sign, and we're going to see how big this difference is from 47 to 34 in light of that standard deviation. So it's 11.079. We'll round to 11.08. How about that? Okay, so the standard deviation without the sign, 11.08. Okay, so without the sign, the speed was 47.84. There we go, 47.84. With the sign, it dropped, I think it was just under 35, 34.62. That'll go right there. Okay, so it's this difference divided by the standard deviation of the before condition. Okay, so let's go ahead and do the math. We did it earlier. It was 47.84 minus 34.62 gives us 13.22. It's going to go right here. Okay, so that's the difference. It decreased by 13 miles per hour. We're going to divide that by the standard deviation, 11.08, and this is going to give us the effect size, 13.22 divided by 11.08, 1.19 is our effect size, 1.19. So now we have to interpret that. Okay, so Cohen's d, it's 1.19. Is that good? We have to use Cohen's criteria. Cohen suggested that 0.2 is a small effect, 0.5 is a medium effect, and 0.8 is a large effect. So 0.8 is large, and we have 1.19. So this is very large, right? It's over a standard deviation, whereas 0.8 standard deviations is already large as is. So this is a big effect. Okay, so let's talk about that. Okay, so 1.19. The effect size of the decrease in motorist speed was 1.19 based on Cohen's criteria. This represented a very large effect, right? So 1.19 is much bigger than 0.8, which is large, so this is a very large effect. What does that mean? So that means, this means that the observed difference was practically significant. it was practically significant. So it was statistically significant, it was practically significant. Before, they were speeding through town at unsafe speeds. Now, on average, cars are going through under the speed limit. It was significantly less. It's unlikely that this was that there really was no effect going on. And we know that the change had practical significance as well. So based on the analyses above, what can we say about the effectiveness of the prompting sign? Okay, well, let's talk about that. All right. So again, I always like to put this in practical language, put it in terms that make sense, everyday language, so we're not just ending with some numbers. We want to interpret those and make sense out of it. So before the prompting sign was erected, the average motorist sped through town going, what was the speed? Let's see here. Going 47.84 miles per hour, which was well over the speed limit. After the sign was placed, the average speed decreased to 64.62 miles per hour, which was under the speed limit. The decrease was both statistically and practically significant. Okay, so all this is to say, this means that the prompting sign appeared to be effective at reducing motorist speed. Okay, it worked. Right? Let's make this as simple as possible. So I kind of recapped all the analyses here, but when it comes right down to it, it worked. We want to be able, when you're doing analysis for somebody, some kind of analysis, you want to be able to kind of boil it all down and say, yes, the sign worked. Now, assuming the experiment is internally valid, is it reasonable to say that the placement of the prompting sign caused motorists to slow down? So there's a couple of things here you want to be very careful about. Internally valid. What does this mean? So internal validity, when you're talking about an experiment, means that it was the independent variable that's responsible for the change in the dependent variable. So remember, independent variable causes the dependent variable, or dependent variable depends on the independent variable. In this case, the independent variable was the sign, and the dependent variable was the speed in miles per hour. If the experiment is internally valid, that means that it was the sign that caused this difference. There wasn't something else going on. For example, time of day. They could have measured, before the sign was put up, they could have been measuring the speed at during rush hour, and then later, after they put up the sign, they measured the speed in the middle of the day, or maybe on a weekday versus a weekend, something like that. That could have been causing the difference. Some other confounding variable. The confounding variable is another variable that varies with the independent variable. But assuming that it is internally valid, nothing else was causing this difference in speed, is it reasonable to say that the placement of the prompting sign caused motorists to slow down? Now, this is the next word that should give us pause. We always have to be very careful when we talk about causality. In a correlational study, you probably heard the expression correlation does not imply causation, or correlation does not equal causation. In a correlational study, you're looking at the association between variables, and we use words like predict or is associated with. And we would avoid using the word cause or effects. So it's asking us, can we use that word here? Can we say the sign caused them to slow down? Or can we simply say it predicted or was associated with this? Right? So the whole purpose, this is an experiment where you manipulate the independent variable The whole purpose of an experiment is to make causal claims. So this is a situation where, assuming it's internally valid, yes, we can say that the sign caused the motorist to slow down. That was the whole point of the experiment. If we had done something like, we found some towns that used the prompting sign and measured there. We found some towns who didn't have a prompting sign. We measured there and then compared those. That would be a correlational study. But we wouldn't be able to say, use the causal language. But since we manipulated this variable, or the town did, right? Since we did this, we manipulated the independent variable. And theoretically, the only difference in speed is what we caused. Then yes, we can say that the sign caused motorists to slow down. So because this was an experimental design in which the independent variable, the prompting sign, was manipulated, we can infer that the sign caused, I'm going to put that in italics, caused the motorist to slow down. If this had been a correlational study, we could not use that word, right? If I found a town that had a sign, a town that didn't have a sign, and compared them, I could talk about it. I could determine whether or not it's sort of consistent with that idea, but I couldn't use the word cause. I couldn't use the word effect. But here, we manipulated the independent variable. This is an experiment. Therefore, yes, we can infer that the sign caused the motorist to slow down. The causal inference is justified. Finally, as a behavioral scientist, what advice would you give to the town regarding the prompting sign? Okay, so now implications of this. What are their options? They could leave the sign up. They could take the sign down. They could add another sign. So presumably, right, if the street goes through the town, right, here's a street, and here's the town, right, maybe they tried the sign here, perhaps, so the motorist going this way slowed down. Maybe they could put a sign on the other side to slow down the motorist going this way, right? So they could put another sign. They could try the sign on some different streets, or they could take the sign down. So they have a few options here. So what are we going to recommend? So why don't we recommend well, they certainly should leave the sign up. It does appear to be working. They could continue to monitor motorist speed and see if this trend continues. And they could also try adding a sign going the other direction to see if they also experience a decrease in motorist speed, people going this way. Right? So that would probably be what I would recommend. I wouldn't take the sign down. It does appear to be helping. It didn't cost very much. It's certainly less expensive than adding a patrol car. Right? It's just a sign. So I would recommend that the city, or what's the town council, right? Town council leave the sign in place as it appears to be working. They should continue to monitor motorist speed to make sure it continues to produce the desired effect. And see, it's possible that the same people might drive through the town and just kind of get used to it and start to ignore it after a while. Maybe because it's a new sign that caught their attention, but after they've seen it 100 times, they might start to ignore it. It's possible. Or this could be people from out of town driving through, and so they don't drive that often through this area. And but then, it's a good idea to kind of keep an eye on things, keep monitoring speed. They should also consider placing a similar sign on the other side of the street to slow traffic coming from the other direction. Probably not a bad idea. So they could give that a shot as well. So motorists going this way, motorists going this way, and they can see how things go. Other side of it, so it's a highway, right? So I always like to look at it in terms of the original. Let's see here. Yes, as the highway enters the town, right? So the highway runs to the small town, right? So they have, the sign working this way. Let's try a sign on that side. We can slow traffic coming from both directions. Hopefully, it'll be safer for the good people of Middleburg. Okay, well, hopefully that was helpful to you. It makes a lot of sense, and good luck as you work on the future lab assignments. Thank you.